Here I have two very similar selective amplifiers. This is the first one I made. You can see details about it in previous videos of this series. This one happened to be the mirror image because I happened to solder the sides on the wrong side of the hole after having drilled the holes for the BNC connectors. Now, that doesn't matter at all. The schematic diagram is very similar, although not quite identical. In this video, I will try to do the best I can to measure sideband noise with precision. And I can run these two oscillators in a interferometric setup. And then I cannot see the noise from one or the other. I will only see the sum of the noise from both of them. But since they are fairly similar, I should be able to guess that they contribute by equal amounts. That will probably... we will see. I have not done it yet. As a first step, I want to establish a power reference. That will be 0 dBm when set on this particular signal generator, this one with the blue label on it. And the power level I want is at the other end of this cable with red BNC connectors. And the best instrument I have for power measurement is the oscilloscopes. So I will use them. They have a 50 ohm input. On channel 1 here I see 612 millivolts, and channel 2 it is very much the same. On this other oscilloscope I can read 620 millivolts on channel 2, 50 ohms as you see, and channel 1 well, it's also 620 millivolts. The average, 0.616 volts peak to peak, that is 0.95 milliwatts, which means the reference power in this connector is minus 0.2 dBm. So the power out from this generator is probably very close to 0 dBm. Now, I look at this spectrum analyzer and it shows something different. It shows plus 0.3 dBm. That's an error of half a dB, and that is perfectly acceptable within the specifications. But I want to be a little bit more accurate than that. But what I see here is important. The overtones are very weak compared to the 10 MHz signal. They are suppressed by more than 40 decibels. That means that taking the peak-to-peak voltage to compute the power, that requires the waveform to be a nice sine wave, and indeed it is, as I can see here. The carrier power is 1 watt, about, but the receiver is saturating at about minus 40 dBm because I have this amplifier followed by that amplifier, and then I will use this receiver without the built-in attenuator. So I need a reference signal at 70 dB below the carrier. So I will check whether I can use the spectrum analyzer or whether I have to use this SDR IP. I have to set the generator to minus 70.2 to get a 70 dB shift in the level from minus 0.2 to minus 70.2. And I will look at the spectrum analyzer, what happens here. I have to set the generator to minus 70.2 to get a 70 dB shift in the level from minus 0.2 to minus 70.2. And I will look at the spectrum analyzer, what happens here. So, at 0 dBm I can read plus 0.37 and then minus 70.2. Now I can read 69.7. This is pretty good, but the signal is a little bit noisy because it's not so high above the noise floor here. Here is the setup. The unit under test delivers about plus 30 dBm. Then I have a 20 dB coupler. It's a bit frequency dependent, but that doesn't matter because I just use it to inject a signal from a signal generator here. Then I have another coupler which is flat and fairly accurate, 20 dB, and then it is connected to the SDR-IP. And I use the SDR-IP to verify that this signal is 70 decibels below that signal. Both pass through here. And then I have a selective load on 10 megahertz that presents an impedance of 50 ohms to the signal source here. And then a quarter wave, because the notch here is a short at the 10 megahertz frequency, so at the other side of a quarter wave there is no load on 10 megahertz here. And then I have two more notches, an impedance match here, by which I can set the impedance that this device looks into close to 50 ohms at the frequency where I am measuring the sideband noise level. And after the impedance match, there are two low noise amplifiers and finally a perceivs. The amplifiers make the noise figure at this point low, very low, which means that the noise figure at this point is rather low, and that's necessary in order to be able to see the noise from this oscillator. Here is the point where I will connect the oscillators. As a first step, I will check the impedance here. Well, you can see it is calibrated. At least it shows infinite when there is... Well, it is properly calibrated. And I have tuned, I will change the scale, 0.3. You can see the two frequencies where I have the markers 1 and 2. These are 10 megahertz and 9.5 megahertz. I'm looking at the frequency separation of half a megahertz. And I can tune the matchbox to move the position of the marker number 2 and make it very close to 50 ohms. It's a little bit tricky, but I come reasonably close. Well, It's not so easy to do this. Well, this is going to be close enough. And, of course, the selective load sets the impedance at 10.0 megahertz, where the marker number 1 is. So now I know that the impedance is correct here. So the sideband noise emitted by these oscillators will meet 50 ohms at the frequency where I do the measurement. The SDR IP is connected to this coupler, and I have the signal from the test oscillator here at 10 megahertz. Occasional glitches, but I don't care about that at the moment. I have calibrated, so it shows 0. And then I switch on this generator at 9.5 megahertz. And I want it to be 70 decibels below. And it's minus 70.12. So I need a little bit more signal. I go in steps of 0.1 dB. Oops. 70.02. That will be fine. Now the signal is 70 decibels below the carrier. And then I switch for the passives, and here we have the same signal, but now through the notch filters and the matchbox and these low noise amplifiers. And I wanted to show, of course, minus 70 here. So there is an error of 0.2 dB, 75.03 maybe. Oops. That was the wrong direction. 75.43. And now I read minus 70. So this scale is now properly calibrated to reference to the carrier. And I switch off the reference signal at 70 dB below carrier, and now what remains is the noise from the device under test. This one, the old oscillator or amplifier, which has a feedback here to convert it into an oscillator. And the noise floor I can see here is minus 164.55. 164.55. And now I disconnect the oscillator and put a 50 ohm dummy load here instead to see the background noise of the test system. And the noise goes down significantly, so I do see the sideband noise. now I have minus 168.10, or maybe 168.11. No, 168.1. Let's call it that. Minus 168.1. So, when connecting the test object instead of a dummy load, the noise increases by 3.55 dB. That's 2.275 times, which means that the noise from the test object is 1.275 times higher than this noise level. And that is 1.05 dB above this level, which means that the noise I find is 167, and this and that cancel. So minus 167.0 dB in 1 kilohertz. Because measurements are made in a bandwidth which is accurately set to 1 kilohertz. You can find that easiest by do it like this. And you can see that the 3 dB points are plus minus 500 hertz from the center. And this means that the sideband noise I have found is minus 197.0 dBc per hertz. And this is the sum of AM noise and phase noise. So, I don't know, but I can guess that this far away the noise I see is just white noise from the amplifiers, so it is equal amounts of AM noise and phase noise. And I connect the generator, the test object, back again, like this, and you could see how the noise level goes up, but not very much. I can stop the oscillator by disconnecting the feedback loop here. And it's obvious that the noise floor doesn't change at all, which means that what I see here is actually the white noise from the amplifiers. It is not flicker noise, so it's not only phase noise, which one can expect at the close frequency separation. So, phase noise 200 dBc per hertz. I will do the same procedure for this other oscillator to start with, just to show the complication. The signal level here is going to be a little bit different. So when I go to the SDR IP and click on the signal, I don't see 0 anymore. They differ by 0.55 dB, these oscillators. So I go through the calibration procedures and get the readings for this one, which is the new oscillator. And then I will do other frequencies and collect the data with this setup at a couple of closer spacings. I use this noise head to check the noise figure at this test point. I have set the noise figure meter for 6.4 dB. And I want the noise floor to change by 3 dB when I switch the noise head off. The reading now is 3.14. and now I get something a little bit less, minus 0.02. So it was 3.1. So the noise figure well, 6.3 is more accurate. I want to know the power of these two devices I'm testing. So I have taken this cable, which is painted red and comes from here. And I know that the power is fairly accurately minus 0.2 dBm. So I have calibrated the S-meter to show minus 0.2 dBm here. And then I connect the oscillators, one and then the other, to see what is the power they deliver. This is the old oscillator, 30.02. And here is the new one, 29.58. I will do evaluation at some other frequencies, but first I will present what I did with the 0.5 megahertz observations. The noise figure is 6 dB, and these are the measured noise levels, as you have seen here and here. Then from the difference here I can compute the noise as I showed manually. The formula for that is convert from decibels to linear power scale for both values, take the difference, and then take 10 times the logarithm and subtract 30 to go from kilohertz bandwidth to hertz bandwidth. And I get this 197.08, and manually I got minus 197. So this seems okay. And then I do the same for the new, and it's not quite as good. It's the same formula but different sources. I have measured the carrier powers, and from the carrier powers and the noise figure I can compute the noise floor, and this is an independent determination, and I arrive at 198.02. Now I can take the difference between this floor and the floor I arrived at by measuring directly in 1 kilohertz bandwidth. And I can take the difference, and it turns out to be only 0.08 decibels. For the new oscillator, the agreement is even better. Only 0.02 dB is the difference. And you can see here what the formula is. And for the other one here, this is the formula. And so I will now make measurements on some other frequencies and put into this Excel spreadsheet. Here is my setup for interferometry. The two oscillators, device under test 1 and device under test 2. There is first a minus 8 dB coupler that is taking out a signal, attenuating by 6 dB and sending it into a mixer. And device 2, there is a coupler, 20 dB, from where I can send a signal, a reference signal, into the system. so I know how to calibrate. Then there is a 6 dB coupler. I happen to have 6 dB and 8 dB, and that goes through a experimentally found length of cable and through a 3 dB attenuator into the mixer. The mixer will give a DC voltage when the phase locking has been successful. The PLL amplifier has a fairly high output impedance, and I have added a very low frequency filter, 2200 microfarads and 100 ohms, to not modulate device under test number 1 with frequencies above a hertz or maybe less. The signal of interest comes from sending the signal further. There is a variable attenuator that can attenuate continuously by something like 0 up to 0.3 decibels. Then a stepped attenuator that can step by 0.2 dB steps, and the signal then goes into a hybrid. And the other device under test goes through these couplers and that coupler, and further one more coupler where I can monitor the amplitude relation between the device number 2 and a test signal that I can inject here. And then it goes into this hybrid, to which the other signal is also going. So the hybrid is getting 2 signals at a signal level in the order of 1 watt, maybe a little less, but not much less. The output of the hybrid has the sum output going this way into a hybrid where the signal is split. Part of it goes to a 30 dB attenuator, and I can connect the SDR IP here to look at what is the sum signal. And that is the sub signal and the sum signal plus that test signal I might inject. And the other part of this hybrid is attenuated by 10 dB. That is to set the impedance close to 50 ohms. And then there is the oscilloscope, channel 2, which I use for the trigger input. So I'm triggering the oscilloscope on this sum signal. The other output of the hybrid, that's the difference, which should be very close to 0 when everything is successful. After is an impedance match, and then the stepped attenuator and one more impedance match. These things are very important. This impedance match is set to make the isolation between the 2 oscillators good. I can set a high attenuation on the stepped attenuator. Then it is very close to 50 ohms at this point. And I then tune the impedance match here and look at this coupler by putting the instrument here for the presence of the signal from the other device, while having set the PLL amplifier for not locking. So I can make the 2 devices not seeing each other by setting this impedance match properly. Then when making the attenuation very low, typically the impedance will not be 50 ohms, so I have to use this second impedance match to make the impedance accurately the same at the input here when the stepped attenuator is set to 0. And then after the impedance match there is a limiter with several 1N 4148 to protect the amplifier. It's an AMC 147. And then a low pass filter, because there are overtones and I don't want to saturate from the overtones. And then a 3 dB attenuator, followed by a hybrid that splits the signal in two parts. One goes to the oscilloscope, the other to a low noise amplifier, followed by the Perseus, where I do the analysis of noise floor levels and signal levels. Here is the oscilloscope, and I tune the PLL amplifier to change the phase, and you can see that affects the signal. Looking at the Perseus, now at this level the Perseus is saturated, so I fine-tune, and at this point, this level here, things look nice, and I can tune the balance to almost perfect, and this is the level I find. So I measure the noise floor. Well, before doing this I should show what calibration, how that is done. I am now looking at this point with the SDR IP. So that means I'm looking at the signal that goes into the hybrid, and it is the pilot tone from this generator and the signal from the device under test. And I'm going to set the level of this inserted signal to 70 decibels below the carrier from the device under test number 2. So here is the carrier, and I calibrate it to show 0. I'm injecting a signal 500 kHz below, 9.5 MHz, and it's visible here, and you can see the level, and I have set the level of the generator to show -70 with respect to the carrier that I have here. So now this injected signal is 70 dB below the main signal here. And I switch for the Perseus, and I have to set the balancing properly to not saturate, and then I can see the level of the signal at 500 kHz below the carrier. I put it into the center of the passband, and then I have to set the calibration to now show not -63, I want it to show -70, like this. And now I switch off that generator to get the noise floor 500 kHz away. And the reading I find is -158.53. Well, I can take some more points. 158.55. I now switch in 40 decibels of attenuation, which means I get the same impedance, but there is no more any signal. And then I look at what is the noise floor now. And I have still a problem with lean rod. I have tried to find it, but not yet. So now I see minus 159.94 or minus 159.91. Averaging more points. The second decimal is a little bit uncertain. Anyway, minus 159.9 will be a good value. Here are the results. The notch filter gives me noise at 500 kilohertz, 100 kilohertz and 50 kilohertz. I cannot go closer without retuning the notches to make a peak, let's say 20 kilohertz from the center. And I don't want to do that. So these are the numbers that come out of the study, as you have seen before. And the sum of those, which is what I should get from the coherent measurement, the interferometer thing, these are these values. And here are the values I actually get from the interferometer. And the difference is up to 1.2 dB, but it is fairly small. And then I can do with the interferometer measurements at much closer separations, down to 1.7 Hertz, although that it might be a little bit uncertain. I have plotted these results here. So the scale is minus 200 dBc per Hertz at the bottom line. And this point for the old oscillator, which is the best one, and I have verified that the noise is white noise by just switching off the oscillation, and the noise stays at the same level, which means that this is AM noise plus phase noise. So the phase noise should be a little bit below minus 200 dBc per Hertz. Then I am plotting the sum of the noise from both of them, a cross for the sum and a circle for the measurement with the interferometer. And they come very close. Here the difference is 1 dB. And then I have plotted the red curve here. That is the phase noise of the Citroën. That's the best oscillator you can buy from Wenzel today, as far as I know. And that red curve is phase noise only. So at this point it might be compared to something below minus 200. And of course I spent far more resources on the oscillator than Wenzel is doing on their much more elegant solution probably. I don't know how they do it, but this data has been published somewhere. I don't have the reference. Anyway, my measurement of the summed noise of two oscillators, AM plus phase noise, compares pretty well with this top of the art at the moment oscillator. So red line is the citrine, and the blue line is the sum of phase noise and AM noise of two of my oscillators. Here at close separation, presumably there is almost only phase noise. So for an individual oscillator, the curve should be 3 decibels lower if they are equal in the amount of phase noise. Something that I don't know anything about. One could be significantly better than the other. But I don't have the tools to find out, and I don't need to, because now I have the oscillators that are good enough to continue investigating other things with them as the base. The interferometric measurement relies on having the two oscillators phase locked. But since the problem at close range is phase noise, it is necessary for the PLL lobe to be very slow. And here is what I see looking 2 hertz from the carrier. And you can see here things go very slow now. The time constant is regulated by this 2200 microfarad electrolytic capacitor with with 100 ohms in series. If I disconnect this, then the leakage current through it changes the phase, so I have to adjust it back to where the carrier is cancelled properly, like that. And then, looking now at the spectrum, it takes some time because everything is so slow at these bandwidths, but as you can see, the noise is now much lower. Also on the color in the waterfall, it starts to come up here. And that is because the oscillators are following each other through the PLL loop. And what I see now is not the noise that an individual oscillator would have, because the noise is cancelled by phase locking. I have placed 10,000 microfarads, a big electrolytic capacitor, in parallel with these 2200. It makes locking much more difficult, but now it is locked and fairly well balanced. And I can read the noise floor at 10 hertz separation here as minus 101, probably with respect to the carriers, but I don't remember how calibration is done. Now, that's not what I'm looking for. I will just disconnect this electrolytic, like that, to see what happens to the noise. And balancing is not affected by that, and it seems noise at 10 hertz separation is not changing either. Maybe something happens within a couple of tenths of a hertz. This white region looks wider, but could also be that balancing was not quite as good. Anyway, it seems that the time constant is slow enough